Okay, so we're going to look at rates of change and kind of, I suppose, that idea of interpreting these rates of change and manipulating and so on and so forth. So, first of all, we're kind of establishing what a rate of change is, and we've kind of touched on this all throughout differentiation, really. It's something that you kind of have been looking at, really, and we kind of said that at the start that differentiation and the derivative in its kind of essence, that dy dx idea, it's the rate of change of y with respect to x. So it's how one variable changes with respect to another variable, and the derivative is this rate of change. So if we have a positive rate of change, we're increasing. If we have a negative rate of change, then we're said to be kind of decreasing. So the rate at which the one quantity is changing with respect to a particular variable or with respect to a different particular thing, if that is negative, then that quantity is decreasing. So the examples we might have is like we just said there, so the kind of general derivative, the rate of change of y with respect to x. You might have the rate of change of volume with respect to time, so that's dv dt. You could have dA dr, which is the rate of change of area with respect to radius, and so on and so forth. What I've said here is it's important to be able to interpret the meaning of the derivative for functions modeling real world scenarios. So what I mean by that is in some of these cases where the function that you're given is relevant to some sort of real world phenomenon. So you might be looking at, say the example here, it's the weight of a tree, or you could be looking at different functions modeling profit for a company or production that they need to have, or we looked at, I suppose, in the max and min problems, you're looking at kind of the box, and if you're building a box or if you're fencing an area and things like that. So we need to be able to not just work out these rates of change, but also kind of comment and interpret the meaning of these derivatives of these rates of change with respect to those particular functions. So if I'm looking at the volume with respect to time, and then I find dv dt, that I can kind of comment on what that means and what it might mean if it's a particular value, or if it's positive, or if it's negative. The other thing to note then is in some cases we'll just be it'll just be said kind of the rate of change, or the rate at which such and such is increasing. And that's typically then with respect to time. And they mightn't always specify in those cases that it's respect to time. But generally, if it's not said, rate of change of something is probably with respect to time. And I suppose one particular way to know is to look at the units. So particularly if they haven't specified that like the rate at which this is increasing with respect to time, they might give you the rate at which this is increasing is 5 meters per second. So you would know by looking at it that it's a distance, it's with respect to time, because it's dt, because it's per second. So that's the other kind of thing that can help us here then in really just getting to grips with these rates of change. And it's important you have this general idea down before we look at the related rates of change, because you have to kind of be able to manipulate and interpret and kind of work with those specific rates of change first of all, before we can start kind of grouping them together and linking them with other rates. So let's just look at an example or two first, and then we'll get into an exam question. So the average weight of an ash tree is given by this function, where x is the height of the tree in meters. We're asked to first of all find the first derivative. So let's just go ahead and do that. So we're differentiating this function up the top. So that's going to give me 4x plus 3. To describe what it means, it's the rate at which the weight is changing with respect to height. Okay, there's nothing really different there, and in fact we probably have written that answer to questions before. We're just now making it a little bit more explicit as what we mean by all of that. So let's look at part 2 now. Evaluate this for a tree of height of 5 meters. So where height, remember height is x. So I'm evaluating the derivative when the height of the tree is 5. So that's 20 plus 3, so 23. What are the units of measurement of W of the rate of change? So to find the units of measurement, we can look at what the rate represents. So it's the rate at which the weight is changing, and the weight is in kilograms, with respect to the height, and the height is in meters. So the unit of measurement is going to be kilograms per meter. Kilograms per meter. Okay, will it be positive or negative? Well, we're expecting that the rate of change is going to be positive, because the weight of the tree is expected to increase as the height of the tree increases. Okay, so that's kind of what I'm expecting. As the weight increases, the height of the tree will increase as well. So Wx is positive. Okay, I can also kind of see that it's positive because looking at the function I have there, we can see it has a positive slope. So it would look something like that going up the way, probably a fair bit steeper really. The slope of 4. And that means the weight is increasing as h increases. Okay, so we're assuming the weight of the tree is increasing as h increases. Okay, let's look at another example. Or no, straight in. Okay, straight into an exam question. Fair enough. So the weekly revenue produced by a company manufacturing air conditioning is seasonal. Okay, so it kind of makes sense there. So they're manufacturing air conditioning and they're saying that that's seasonal because obviously when it's warmer, maybe there's more demand for air conditioning. The revenue can be approximated by the function. So revenue is profit, or not revenue is not profit. Sorry, revenue is the money made. And we're told this is in euro. So this function, or t, is in euro. We can see that t obviously is probably time. It's the number of weeks. Number of weeks from the beginning of July. Okay, so that could be important for us here as well. Another thing to note here is we can see that we have a lovely trig function here, and we're given our angle in radians. Okay, so important as well for us to note that if we're using angles or if we're working with values of t here, we're probably going to be getting, or working with our angles overall there, we're probably going to be getting radians in our answer. So just making sure that we kind of adjust for that as well. So find the approximate revenue produced 20 weeks after the beginning of July. Okay, and give your answer correct to the nearest euro. So we're looking for the approximate revenue that I have from this production, I suppose from the production here after 20 weeks. So that means here that t is going to be 20. Okay, my time that I'm looking at is 20 weeks after the beginning of July. Remember, t was the number of weeks after the beginning of July. So I'm just going to be finding my revenue after these 20 weeks. So I'm simply subbing in to my formula for 20 weeks. So pi over 26 by 20 plus 37500. Okay, and I can just take my calculator then and complete that calculation, I suppose. So 22500 cos, making sure my calculator is in radians here, and it is, so just doing the same for yourself there as you're working through this one, just making sure it's in radians. 26 multiplied by 20 there, the number of weeks, plus 37500. Okay, and I'm getting an answer of 20.658.50817, and if I round that up to the nearest euro, that's going to be 20,659 euro. I'm putting my euro sign as well, just to show my whole units. Okay, if I'm given units in the question, I need to use those units in my answer also. Okay, so that's our answer for the first part. Okay, find the two values. Two values to me is immediately suggesting quadratic. It's immediately suggesting quadratic to me, but maybe not. It could be, particularly, I suppose here we're looking at trig functions, so we could be looking at a trig equation. Two values of the time t within the first 52 weeks. Within the first 52 weeks, when the revenue is approximately 26,250. So let's have a look at this. So I want to find t when the revenue is equal to this amount. So we're going to have to take our revenue function and we're going to set it equal to this amount of money. Okay. So first of all, we're trying to get the angle part, the trig function part on its own here so that we can do a kind of trig equation. So we're going to start by kind of moving all my numbers, I suppose, over to one side. 11,250. So cos of pi 26t is equal to, I'm going to divide by the 22,000. So 11250 divided by 22,500 gives me a half. So I get minus a half. So I'm now looking to see, I'm looking to solve this trig equation, and looking at the trig equation, revising our trigonometry here as well, we can see that the angle here is negative. Okay, the angle is negative. So if we remember from our trigonometry work, that requires me to use my cast circle and look where cosine is negative. Cosine is negative in this section and is also negative in this section. I'm going to be using my little reference angle idea here as well. So I have cos of my reference angle is equal to a half, and that's going to tell me that my reference angle is cos inverse of a half, which is pi over 3. So that's my reference angle there. So working out my two other angles, so this first angle here, that's going to be pi minus pi over 3, which is 2 pi over 3. It's 2 pi over 3. Okay. And looking at my other example here, so we can take it from kind of either side, I suppose, but if I work the whole way around to this aspect here, if I work the whole way around, then that's going to be pi plus pi over 3, which is going to be 4 pi over 3 as my two answers. Now those are my two answers for the kind of with reference to my reference angle there. So those are kind of two values for my pi over 26t being equal to 2 pi over 3. So if I rearrange that, multiply by 26, divide by pi, so 2 pi over 3 divided by, we'll just put it all together, pi over 26, and I get an answer of 52 over 3. And for my other option, pi over 26t equals 4 pi over 3, and we get an answer of 4 pi over 3 gives me 104 over 3. Okay, so the two times where my revenue is going to be approximately those values is when I'm 52 over 3 weeks and 104 over 3 weeks. So you can see they're pulling in trigonometry, pulling in trig equations, maybe not where we expect them to be coming up. And you can see even paper 1 here, like trigonometry, maybe typically a paper 2, but also trig functions can be paper 1 quite a bit, and then you can pull in trig equations with that also. So those are kind of the big parts of trigonometry. So let's look now, we're looking at the derivative, so we are only now getting to some calculus really. So let's find the derivative of this function. So if I'm differentiating this function, I have to differentiate the cosine part, my function part, and I have to differentiate my angle part here also. So first of all, the cosine part is going to go to minus sine. So let's just take this here. So minus sine of pi over 26t. And then I must remember to multiply by the derivative of my angle part, which is the pi over 26 here. So organizing all of that out then, and just kind of rearranging, I suppose, accordingly. So we get 225,000 divided by 26 there, and not really giving me anything too exciting, to be quite honest. But let's just find, so let's just rewrite it, I suppose, in that form regardless. So 11250 over 13 pi sine pi over 26t. Okay, so the general idea there still holds, okay, the whole way along. So now that we've found the derivative, we need to show that the revenue is increasing 30 weeks after the beginning. So increasing means that the derivative is going to be greater than 0. It's increasing if the derivative is greater than 0, 30 weeks. So when t is 30, I want to evaluate my derivative. So using my answer from the previous part, minus 11250 over 13 pi sine pi over 26 by 30. And I can substitute all of that into my calculator. Just being careful, I suppose, with our calculator work as per usual. Let's Multiply by sine, oh sorry, I'll bring that down, sine pi over 26 multiplied by 30. Keeping everything as clean as we can, I suppose, as nice and tidy as we can, we get an answer of 1263.44. Okay, if we round to 2 decimal places there. That is greater than 0, so therefore we can say that the revenue is increasing after 30 weeks. Okay, so the revenue is increasing 30 weeks after the beginning of July. Okay, so looking at the last part now is going to require a little bit more trig equation for us here. So we're finding the value for the time t when within the first 52 weeks when the revenue is at a minimum. So revenue at a minimum, we're looking to minimize or put our derivative equal to 0. So looking at our derivative here, it's 11250 pi over 13 sine pi over 26 t. We want that equal to 0, which means I can eliminate or divide across by the coefficient there to get rid of it. And I get sine of pi over 26t is equal to 0. Sine of pi over 26t is equal to 0. Okay, so having a little look now at what this means, okay, we can use our trigonometry, we can use our reference angles here as per. So we're looking for a reference angle that's equal to 0. That gives me an overall answer of 0. Okay, so I have to be careful with these ones because I don't get the same options, I suppose, or the same ideas as I do when I use my reference angles for other values. So we kind of have to be a little bit more kind of smart about it and look at our look at our unit circle and see the values where my sine function could have a value of 0. And if we kind of relate our sine function to our trig graphs there, okay, so if we're kind of lining these up together here, we should know that our sine function is 0 at the beginning, so that's here, so that's at 0 degrees, and it is also 0 again when it gets to here, and that's when it gets halfway around again, so that's when we get over to here, so that would be at pi degrees. And then similarly when we get back around to here, remembering that a full circle is 2 pi degrees. So obviously if I was to continue on, then again I could get to another kind of go at that 3 pi, 4 pi, so on and so forth. But if we look at those options that we have there, okay, taking sine inverse of 0 gives me just gives me 0. Okay, so now taking, instead of my reference angle, taking my actual value, which is the pi over 26, I'm going to say that's equal to 0, which would mean t is 0, but I'm going to use those other options that I've identified using my unit circle, which is that it could be pi, meaning that t would be 26, or it could also be 2 pi, which would mean that t is 52. Now we were asked within the first 52 weeks, so that's what we've come up with here. 26, 0, 26, and 52. Okay, if we're kind of looking within the first 52 weeks, we might just be taking the 26 there in that case, okay? And in fairness, in this question, they have asked us to verify using the second derivative. So perhaps the second derivative will tell us the specific values there that we could be using. So if we look at our second derivative test, okay, kind of noting as well that if we're looking within the first 52 weeks, we probably will be disregarding the actual 52 weeks itself, because well, that's kind of within the first 52. So we'll get our second derivative here. So that's going to be minus 11250 over 13 pi cos pi over 26 t multiplied by pi over 26 multiplied by pi over 26, which is going to give me an answer of, let's see, can we simplify this down a little bit more, hopefully, 1 over 26, 11250 over 13 times 1 over 26, okay, not all that much, but okay, minus 5625 over 169 pi cos pi over 26 t. Okay, and we want to kind of verify or evaluate that now at our different values. So the first value we have is just 0. So 5625 pi over 169 cos pi over 26 by 0. And evaluating what that gives me then is 69 cos pi over 26 by 0 gives me an answer of minus 104.565, which is less than 0, which implies t equals 0 at a maximum. So that's out of the running. Okay, looking then at, if we evaluate it at 26, 25 pi over 169 cos pi over 26 times 26. Okay, so evaluating that again, but changing this to a 26, gives me a value of 104.565, which of course is greater than 0. Now, if we think about as well what we did with our unit circle there, we did investigate 2 pi, but in terms of our function there, 2 pi is going to line up with 0 in terms of the angles because of the period of the function. So in fact, if we try the 52 weeks, we're actually just going to end up with the same answer of it being back at a maximum again. So in fact, the revenue is minimized, because that was the function, at 26 weeks. Okay, the revenue is minimized at a time of 26 weeks. Okay, so a tricky enough last part there for that question. Definitely tricky enough there, working out how to minimize that function. And as I say, these rates of change, a lot of this is just relating these functions to real life situations and modeling and investigating kind of how they model real life scenarios and all of that and kind of everything that goes with that. So let's look at the next example question. So water is flowing into and being removed from a tank. The volume of water in the tank is measured on a daily basis starting at day 0. The volume of water in litres can be modeled by this formula. Use the function to answer the following questions. Find the value of t when the tank empties. So we want to know what's t when the volume of water in the tank is 0. We want to know what's the answer. So let's take our equation here, putting it equal to 0. I'm going to divide across by -1. And if I factorize that quadratic, I'm just going to jump straight to the answer here to kind of prioritize the other parts. I get 3t plus 4 and t minus 15. So that's going to give me that t is -4/3, which of course can't really be the case. So we're going to have to go with t being 15. So it takes 15 days for the tank to be fully emptied. Find the rate at which the volume of water in the tank is changing when t is equal to 5. So we're finding the rate at which the volume of water is changing, so that's going to be the derivative. So that's 41 minus 6t. We want to evaluate this when t is 5. So subbing in there, 41 minus 30 gives me 11. And it's 11. What rate are we measuring everything in? Liters per. Okay, after 5 days, or when t is 5, I suppose, we are changing rate there at a rate of 11 liters per day. Okay, the volume is changing at a rate of 11 liters per day. Another example there where no units there was a loss of 1 mark. Find the value of t when the volume of water in the tank is a minimum. So, our maximum, excuse me. So we're looking to, first of all, set that equal to 0. So I'm setting my first derivative equal to 0. That's the 41 minus 6t, which is going to give me that t is 41/6. Let's just confirm that that is a maximum. Okay, so second derivative is negative, which confirms that that gives me a maximum. And we want to now find that maximum volume of water. So we're going to find the volume for t equal to 41 over 6. Okay, so subbing that into the original function, 6t plus 41 by 41 over 6 minus 3 by 41 over 6 squared. Okay, and that is going to give me, let's evaluate, 41 by 41 over 6 minus 3 by 41 over 6, so 41 over 6 squared. It's going to give me an answer of 200.083, which to the nearest litre is going to be 200 litres. So the volume of water is 200 litres, the maximum volume of water, 200 litres, okay? So lots of different questions going on there, lots happening, particularly, I mean, one of the main problem areas or the main kind of tricky areas there would say that first question is the trigonometry part of it, or the trigonometry aspect. Definitely a difficult kind of question to tackle there, but when you've revised your trigonometry and have kind of gone over those bits, it definitely would be a little easier. But it's just kind of keeping everything straight in your head, I suppose, and keeping, even though we're differentiating trig functions there, that we're keeping it kind of consistent the whole way through. The second one, a much nicer example of a rate of change question, I suppose, that's a little bit more straightforward. We're going to look then in a separate video at the specific ones for displacement and velocity and acceleration, as they're just kind of just maybe a little bit more specific, so we'll just kind of go over them in a little bit more detail then as well.